Welcome to the deep dive. Today, we're jumping straight into the deep end of storage administration, really getting into the technical details.
That's right. We're looking at some very specific on-and-tap scenarios today.
Yeah, we've got this analysis kind of based on practice questions for the NS0-593, focusing on ONTAP OS, hardware, protocols, performance, the works.
And the idea isn't just exam prep, right? It's about using these focus problems as a shortcut.
Exactly. A shortcut to understanding the really critical admin and troubleshooting stuff. We want those aha moments.
Mm-hmm. So we'll hit the what's the fix, but also crucially the why. What's the system logic behind it?
Right. Distilling that essential knowledge you need when things go sideways late at night. So let's dive in. First section, core diagnostics, performance bottlenecks. Where do we start?
Okay, let's start with something fundamental. Auto support. Essential service, right?
Definitely. So the scenario is auto support messages just aren't sending. But, and this is key, the admins check the network, ping works, routes look good, connectivity is confirmed.
Classic problem. Wires seem fine, but no data flows.
So where do you go next?
Well, before you double-check the network again, you have to ask, is the system even trying? Is the service actually configured to run?
Okay. So check the source first.
Precisely. The direct action is to run system node auto support show. You need to look for that auto support on field. Is it true? Because if it's false, well, that's your problem right there. Network connectivity doesn't matter if the tap is turned off,
Good point. Check the main switch before tracing all the plumbing. Okay, let's go deeper. Hardware level. An unexpected node reboot happens.
Right, the scary kind.
Yeah. And you suspect hardware may be a power spike, maybe overheating. The main OS, ONTAP, it just dropped. Where do you find the absolute ground truth logs for what happened right before the crash?
Okay, this is where you need to think about the system architecture. What's still running when ONTAP itself might be, well, unresponsive?
Something lower level.
Exactly. The service processor.
The SPC.
The SP logs, right. CS log
Oh,
cell. That's the one. Think of the SP as the system's flight recorder. It's black box.
I like that analogy, black box. So why is that log more reliable in this specific case than, say, the standard system event logs?
Because the SP is essentially a separate little computer. It has its own micro OS, totally independent from the main ONTAP running on the node.
Okay. So it keeps ticking, even if the main OS stumbles.
Precisely. It's monitoring the low-level hardware, the environment voltage, temperature, fan speeds, that kind of thing. It captures those events even when ONTAP is crashing or completely offline. If you suspect a physical issue caused the reboot, the SP log is your first stop. It has the final moments recorded.
Got it. Independent system for independent verification. Makes sense. Okay, let's switch gears from failure diagnostics to performance. Latency, always a fun one.
Oh yeah, everyone's favorite guessing game.
So you're troubleshooting high latency. You look at the counters, you see this data latency is like through the roof, really high. But Netshare latency, it's low, negligible, almost zero.
Okay, that pattern tells you a lot immediately.
What's the instant conclusion? What can you rule out straight away?
The network. If Netshare latency is low, data is getting between the client and the storage controller's front end nice and fast. The network path itself isn't the bottleneck.
So you can tell the network team to stand down, basically.
Pretty much, yeah. The high disk data latency points the finger squarely at the back end. The delay is happening down at the physical storage media level. The disks, the SSDs, they're the ones taking too long to respond to the I/O requests.
So it's a storage media response time issue. Clean isolation using just those two metrics. Very efficient.
That's the goal. Pinpoint quickly.
All right, let's move into our next section. We're looking at protocol configuration traps, access control, some places where rules are really, really rigid.
Ah, yes, the land of you can't get there from here configurations. Immutability is key here.
Exactly. Let's start with a SAN scenario. An admin maps a LUN using ISCSI, standard stuff, but the host just cannot see it, can't discover the LUN.
Okay, troubleshooting time.
Right. And they figure out the initiator, the host trying to connect, was added to an I group. But that I group was accidentally created with the protocol type set to FCP fiber channel, not ISCSI.
Ouch. Mismatched protocols.
Yeah. So the admin thinks, okay, simple fix. I'll just edit the I group, change the protocol type to ISCSI. But nope, system says no. Why and what's the actual fix?
The why is fundamental. An I group's protocol type is immutable. You set it once at creation, and that's it. You cannot change it later.
Never. Not even with some hidden admin command. Why so strict?
It's about stability and predictability in the SAN fabric. FCP and ISCSI are completely different worlds. Different physical layers, different addressing, different login processes. Allowing a live switch could cause, well, chaos for any other initiators potentially using that iGroup. It's a safety mechanism.
Okay, so it's intentionally rigid to prevent accidental fabric meltdown. Makes sense. So the fix must be.
No way around it. You have to delete the incorrect FCP iGroup entirely. Then you recreate it from scratch, making absolutely sure you select SE as the protocol type this time, then add your initiators back.
Start over. Do it right. Got it. That immutability rule is a big one to remember. Okay, sticking with the SAN, let's talk fiber channel ports. A port is physically connected. Link light is up. Port show says the physical state is up.
Good start. Cable's plugged in.
But the logical state is stuck at offline. It won't come online logically. Hardware seems fine. What's the most likely culprit outside the storage system?
Right. If the physical connection is good, but the port won't complete its fabric login, the problem is almost always upstream on the FDC switch.
Zoning.
Bingo. Most likely cause. The zoning configuration on the switch is missing the WWPN, the worldwide port name of that specific ONTP FC port. Zoning controls who can talk to whom on the fabric. If the ONTP port's WWPN isn't in the right zone, the switch won't let it log in logically. Doesn't matter if the cable's perfect.
Another case where storage admins and network admins need to be best friends. Okay, shifting from blocks to files. NFS access. Identity issues.
Ah, name mapping. Always fun.
So a user gets permission denied on an NFS share, but the admin checks and the UNIX permissions on the file system look totally correct. And the user is authenticating via LDAP, and that seems to be working too.
Okay, so permissions look right, authentication seems okay, but access denied.
Yeah, where's the breakdown likely happening?
If it's not the permissions themselves, it's almost certainly about identity resolution. How does the SVM figure out who this user actually is, especially when you have multiple sources like LDAP, maybe NIS, local files?
You mean the order it checks them in?
Exactly. The name mapping configuration lookup order is critical. The SVM has a sequence check local files first, then LDAP, then maybe NIS, or whatever order it's set to.
So if it's set to check, say, local files first, and the user isn't defined locally,
it might just stop there. It might fail the lookup before it even gets around to checking LDP, where the correct user identity and group memberships actually live. The result: access denied, even though the user exists correctly in LDP, and the file permissions would have been fine if the system had mapped the identity correctly. That lookup order is paramount.
That's subtle but crucial, the order of identity checking. Okay, let's push into security overrides, specifically with S3.
Object storage policies. Yeah, these can get layered.
Right. An application is using S3 on ONTAP app. It tries to delete an object, gets access denied, but the user account the application is using seemingly has all the necessary permissions, maybe through group membership. Full control, looks like. Should work, but doesn't.
So how can a user with apparently sufficient permissions still be blocked from doing something like deleting an object?
This boils down to the rule of precedence in security policies. Explicit denial almost always overrides general permission.
Meaning, even if the user or their group has broad permissions, there's likely a more specific S3 bucket policy in place. And that policy probably contains an explicit deny rule for the S3 delete object action targeted at that specific user or group, or maybe under certain conditions.
So a specific no you cannot delete rule in the bucket policy trumps the general yes you can do things permission the user has.
Precisely. Denial wins. It's a common security pattern. Always check the bucket policies for specific deny statements if you're getting unexpected access denied errors, especially if the user permissions look okay otherwise.
That's a huge tip for troubleshooting S3 access. Check for those explicit denies. Okay, let's use this idea of central control and overrides as we move into our final section. Cluster management, system architecture.
Right, zooming out a bit to cluster-wide operations and design principles.
Let's talk software management. Downgrading on ONTAP. Say you need to roll back from 9.12 to 9.11 on an HA pair.
Okay, a rollback scenario.
You've done the prep. The target image, 9.1, is copied onto both nodes' boot media. What's the single command you run, cluster-wide, to actually commit to that downgrade and tell the cluster, okay, next boot, use 9.11?
That's the cluster image switch command. It's the central command for managing the active software image across the entire cluster.
So it handles coordinating both nodes in the HA pair.
Yep. It updates the boot parameters on all nodes in the cluster, telling them which image to load on the next reboot. It ensures consistency and orchestrates the process so the cluster comes back up on the desired version. It's the definitive switch version command.
Okay, cluster image switch, got it. Now, back to performance, but this time about controlling it. QoS.
Quality of service, putting limits in place.
Right, you've got a workload, maybe some big data job, and it's just hammering the system. Monitoring shows it's causing a clear CPU contention bottleneck across the cluster, not storage I/O, but CPU.
Okay, the processors are overloaded because of this one workload.
Yeah. So you decide to use QoS to rein it in. What specific QoS policy restriction is the most effective way to tackle a CPU bottleneck directly?
Good question, because you could limit IOPS,
Right.
or throughput.
Right.
But if the problem is CPU cycles...
Those might not help much, or could even just starve the process weirdly.
Exactly. To directly address the CPU contention, the most effective QoS control is to limit the volume's maximum CPU utilization percentage. You're putting a cap specifically on how much processing power that workload is allowed to consume, freeing up CPU for other things.
Match the control to the resource constraint. Limit CPU for CPU problems. Makes sense. Okay, final big architecture topic. Metro cluster. Specifically Metro cluster IP and disaster recovery scenarios.
Like stake stuff, keeping data available across sites.
Definitely. So imagine a Metro cluster IP setup. One site experiences a major failure, it goes down. But automatic switchover, AUSO, which should kick in, is prevented. It doesn't happen. And the reason given is that the tiebreaker software, that third-party witness component, was offline at the time.
The tiebreaker was down. That's critical.
Why? Why does the system refuse to automatically fail over to the surviving site if it can't talk to the tiebreaker? It knows the other site is down, right?
It suspects the other side is down, but it can't be certain without external validation. The tiebreaker provides that essential external quorum, that independent vote.
Quorum, meaning proof that it's a real site failure, not just a network split.
Exactly. Without the tiebreaker's confirmation, the surviving site can't be absolutely sure that the other site is truly dead and not just temporarily isolated by a network issue, but still potentially active.
And if it switched over automatically and the dead site was actually just partitioned,
you could end up with split brain. Both sites thinking they own the data, both potentially accepting rights. That leads to data divergence, massive corruption. It's the nightmare scenario.
So the system refuses AUSO without the tiebreaker to prevent split brain at all costs.
Absolutely. Data integrity trumps automatic failover in that situation. The lack of tiebreaker communication forces manual intervention to ensure the state before initiating a potentially dangerous switchover.
Wow. That really highlights how vital that external tiebreaker component is. It's the safety lock against data corruption. Right. So for you, the listener, to think about, the disaster happens. AUSO fails because the tiebreaker is down. You, the administrator, have to take over manually. What are the specific non-automated commands or verification steps you need to perform under pressure to safely confirm the site failure and then manually trigger the switchover, all while guaranteeing you don't cause that dreaded split-brain data corruption?
What checks give you the confidence to push the button? Something to chew on until our next deep dive.
Thanks for listening.